Hey everyone, Hugo here. Thank you so much for joining. I'm dialing in from Sydney, Australia, actually. So I presume most of you on the West Coast at ODSC West, but I've spoken at different ODSC conferences for years, and just want to thank the organisers for having me back. It's always a pleasure, and thank you all for joining this session as well. I see nearly 30 people in the proverbial room, and it's great to. We'll be talking about generative AI. To actually deliver business value and moving from prototype to production in several senses of those terms. I'm head of developer relations at Out of Bounds, where we work on productivity tools for data scientists. So you see here a data scientist building their models and reaping the fruits of their labor up in the top of the tree while they're being supported by a big stack of infrastructure and a platform engineer or infrastructure engineer down the bottom there. And so Metaflow is a framework that my colleagues built at Netflix in 2017 and open sourced in 2019, and now it powers machine learning and AI at hundreds and hundreds of organizations around the world. And we just want to make sure that data scientists have the tools that they can build the models they want and have access to all the cloud infrastructure, all the versioning, all the orchestration tools they need without having to write a whole bunch of configuration and YAML and these types of things. So we'll see how that plays out. But let's, sorry, I'm just getting over being slightly ill, so give me 1 second. So what I want to talk to you about is thinking through how we can embed generative AI foundation models, large language models into traditional software systems, into enterprise stacks, and how data scientists can actually use them in production software. But before we get there, I kind of want to look at traditional software, think about what we need from it, then look at machine learning and then what changes with machine learning, then look at generative AI and reason about what changes with generative AI then. So there are many things we require from traditional software. Three are really important ones, that it's a valuable system, that it delivers business value. Also that it runs reliably without human supervision. So when I go to dinner and sleep at night, I can close my laptop and this software in production is still running. We also want it to produce correct results, right? So the question is, what changes, if anything, when we introduce machine learning and data science into the system? So we've got a few new things, right? We have data coming into the system, so we're introducing kind of the entropy of the real world, which means that the tightly scoped tests of traditional software perhaps aren't quite as relevant, and we need to be thinking more about monitoring in real-time machine learning systems. We also have machine learning models enter the valuable system. On top of that, we have a new role. We have a data scientist, which is, as we now know, very different in a skill set and what they want to be doing from your traditional software engineer. So how does this change the stack of software when we move to ML-powered software? So let's think through what the building blocks of machine learning systems actually are. So we have models, we have data, and we have code, and we have a data scientist working with all of these. Now, for models and data to work together, we require some sort of compute layer, and that may be on your laptop. If we're promoting things to production, perhaps we want something running on a server, or we also, require cloud resources. Think about, large-scale parallel training or hyperparameter tuning of different models. You may even want GPUs for that. Pardon me. It's also springtime in Sydney, so the pollen is out to get you. Okay. As we build more and more complex models, we'll start to require orchestration tools. So write essentially graphs of all the different flows, maybe machine learning flows. Maybe we're preparing features for 3 different models. Then we do more feature preparation for one. Then we train them all in parallel. So we'll start to require orchestration tools. The other thing is we've got a human building these things, right? So we need things, infrastructure and developer-friendly UXs, which really speak to these humans' needs. So how do humans build ML systems? Well, they build them iteratively, right? So data scientists and machine learning engineers will do rapid prototyping, perhaps even in a notebook. So they'll build models, and then they'll want to look at the results of those models and look at the data and the output and these types of things. So we need to version our models now. So we're not only versioning code like in traditional software, we're versioning models, we're versioning code, perhaps even versioning data as well. And then we need to figure out how to deploy models. So this speaks to when I do close my laptop at the end of the night, making sure that my model is deployed in such a way that it feeds into this valuable system while I'm asleep. So this leads to a new vision of what the software stack looks like when it's machine learning powered. So we've gone through several of these: data, compute, orchestration, versioning, deployment, and modeling. And the truth is, most scientists and machine learning engineers really want to focus on the top of the stack while requiring the infrastructure at the bottom of the stack. And there's often a question here that is, wait, don't data scientists really care about the data? And the answer is, of course they do. You're absolutely right. What we're really referring to here is kind of all the data engineering infrastructure and all the data engineering pipelines. And a data scientist doesn't necessarily care if their data is coming from some Parquet shards in S3 or Snowflake or wherever it may be. They want to have the data in order to be able to work with it. So that's why data scientists don't really care about where the data's coming from or what forms it's in, or how it's been engineered. They want to work with it in order to build models. But there is a huge amount of infrastructure required at the bottom of this stack. So because my understanding is this is a technical audience, just to give a sense of how we work with this stack in Metaflow. This is some relatively standard Metaflow code where we have our imports, then we define our machine learning workflow via a class. And each step in the workflow we define as a step using the @step decorator. And this is a toy example. We're not accessing cloud resources, or we actually are here with the @Kubernetes decorator, but we're not drawing data from the cloud or anything like that. So data we're able to work with in steps using instance variables and passing them between steps, and all of that is versioned automatically. The compute layer is, once set up and provisioned, incredibly easy to access. You can use a Pythonic decorator to specify what cluster and how much memory you want, for example, and you can do that at a step level or at a flow level as well. The orchestration story is told by this DAG. So in this toy example, we have a start step and an end step, but you can have lots of steps in between, of course. Versioning is done by assigning these instance variables. So anything you assign to an instance variable in a step will be versioned. You can see, to deploy your model, all you need to do essentially is add an @schedule decorator. If you want to do it daily, you just add that to the top. And then on top of that, for dependency management and modeling, you can specify any packages, any machine learning modeling packages, or anything you want at a flow level or at a step level as well. So that was kind of a whirlwind tour for how Metaflow thinks about it and deals with it. But what I want your takeaway to be here essentially is that you can write pure Python code. You don't need to be writing YAMLs or configuration files, or mucking around too much with AWS and this type of stuff, right? So what we want to make sure, and what Metaflow tries its best to do, is help you write the code you want to write in order to build the models you want to build while being able to access the infrastructure you need. So we've talked about machine learning workflows. How does all of this change? How does generative AI change these workflows? So let's first look at a typical example, which contains a set of sub-examples of how you may think about using generative AI in your production workflows. So currently, we really have two types of ways to use foundation models. We have open source foundation models, and we have AI vendor APIs. So here, think of Stable Diffusion or Llama 2 or that type of thing. Here you can think of ChatGPT, right, or any other number of vendor APIs. And you may take an open source foundation model and fine tune it and feed those results into a customer service chatbot. You also may use it to build LLM embeddings, which you use for the chatbot, but you also use for personal recommendations, which go into a different product. You also have a data warehouse feeding into a lot of these processes as well. You may have an AI vendor API, which allows you to generate images, which then you store in cloud storage, then you leverage for your product as well, right? So one thing I do want to point out is that when you do this organizationally, you are going to need to start thinking more and more about where you want your governance boundary to be. What I mean by that is where you put the things you have governance over and the things you don't, right? So for example, here, the AI vendor ChatGPT API is outside your governance boundary, as is an open source model that someone else has built, right? When you fine tune it yourself, you can control that, but you want to start thinking about, because there are concerns around what your models do, what they're trained on, and then also what type of data you're feeding to APIs as well. So there are significant privacy and security concerns as well. So this is one way to think about kind of how we're productionizing and seeing the productionization of generative AI models. And so the reason I wanted to frame it like this is to suggest that the stack doesn't necessarily change. Some of the details change, right? But we still have significant data concerns. Data is still incredibly important. So we can see in data flowing in DAGs here, we can see we require secure access in our data warehouse. We can see we require fast cloud APIs, right? So the data layer is still as important, if not more important than ever. Compute, we can actually say, is significantly more important now, right? We do require, like a lot of this stuff requires GPUs and big processors, parallel processing and low latency APIs as well, right? So compute is still incredibly important. Orchestration. We need our workflows to be able to react to new data coming in. We need to be able to solve failures gracefully. And we need to be able to checkpoint our flows and resume them at various points as well. The versioning story. So we still need to version code and models and data. But I feel like the versioning story becomes very interesting here, because we need to start thinking about versioning a lot more unstructured data, right? In terms of, as it says here, prompt management, the results of conversations with LLMs and so on. We also, things are personalized, will require isolated namespaces and still very much require versioned artifacts. The deployment story is still as important as ever. We need to be able to promote things to production. We also, and this is something we work on a lot, need to think about event-driven ML. So when a training flow finishes, then that triggering, kind of an event bus system, that triggering an inference flow or prediction flow. If we have data updating daily, then each time it's updated, that re-triggering, what happens with our embeddings, for example. And this speaks to having kind of workflows of workflows, or DAGs of DAGs. We need to be tracking lineage as well. So all of these form part of the deployment story. As ever, we want data scientists and machine learning engineers to be able to use the models they love. So use third-party models, such as the ones we've already talked about, open source LLMs, such as the Llama family, Llama 2, Stable Diffusion, which we'll get to, these types of things. You'll need custom models, so use your own libraries, as well as calling external APIs. Another thing that you really need to think through is you need to do all of this in a manner that makes engineers happy. We'll need data governance. We're going to need cost efficiency, integrations, audit and access control, high availability, and we need to think about the software supply chain as well. So what I want to do now is really think through some use cases of generative AI in the context I've set, and think through how this allows us to move towards generative AI systems. Okay, so this is the slide that Lauren was excited about. So generative AI, Stable Diffusion lit the generative AI fuse in August of last year, captivating a lot of people with its ability to leverage recent advances in text to image and the diffusion approach to training neural nets. So we have a blog post around this. If you go to Out of Bounds blog or even just search parallelizing stable diffusion for production use cases, we have a blog post talking about how you can use stable diffusion to build machine learning systems to make many inferences in parallel in the cloud. So this is a figure of how we're doing that. You can see all the different using Hugging Face and Metaflow and Dockerization and cloud resources and that type of stuff. And we're actually parallelizing image generation of celebrities over style. So that's why we have Nick Cage in a variety of different styles there. I'm going to skip going through this video just in the interest of time. So then a month after Stable Diffusion, OpenAI released an open source speech to text model, Whisper. And you can check out our blog posts on that, but essentially these are ways to productionize speech to text and organize your workflows so that they run on Kubernetes so that data scientists can work with them. And we'll jump into a few more details soon. Now, these two models were huge, and these two types of workflows were huge, but then the LLM craze came along with ChatGPT and was just orders of magnitude larger, okay? So while pre-training these models can cost a lot, we chose to research techniques like instruction tuning and fine tuning that continue training the models on specific tasks, following relevant instructions. And these are ways that you can, pardon me, sorry, that you can use such models for your own cases. And on top of that, we've done a lot of work that I'd encourage you to check out on retrieval augmented generation. And this is a way you can use models without having to fine tune them, but how to use your data to guide them. And it's a way essentially of controlling LLM response by approaching the problem at inference time. So those are a few of the things we've been thinking about in terms of productionization. I do want to talk about how these techniques actually make Gen AI valuable. And I understand that, I'll wrap up in a few minutes so we have time for a couple of questions. But we do have significant challenges with how to use them. We know large language models hallucinate. We know that when we get new data, we need to update them. We know that we need to make decisions around closed versus open APIs, and we know how expensive fine-tuning is. And we've suggested some ways forward here. So for the hallucination challenge, we've done work on augmenting LLM context with your data. The data freshness challenge can be solved by scheduling and event-based workflows, which I spoke to already. In terms of like switching out and choosing between closed versus open APIs, we want to make sure, Metaflow wants to make sure that you can reuse workflow abstractions in order to plug and play the models that make sense for you. And in terms of the expensive fine tuning, we really need to think about model optimization. So let's just talk about the hallucination issue. What we see here is we've asked ChatGPT to tell us how to specify conda dependencies in a flow. And it's given a response which is not true. As we saw earlier, you are just using that conda decorator. This is essentially telling you how to do it in a different setting. So this is not true. So this is something we need to figure out. So how do we do that? As I've hinted at it already, to get a more relevant response, one way to do that is instruction tuning. So what this is continuing to train the model using a much more tightly curated data set, teaching it how to do specific things like follow instructions. And so compared to the size of pre-training data sets, doing this can drastically narrow the model's scope and lead it to generate much more relevant responses within the domain of the fine-tuning data set. Another way of dealing with this, as I've mentioned already, is using retrieval augmented generation. And this, essentially, it's extending prompt engineering to provide the model facts when you're asking it at inference time that it can use as a context for its generated response, okay? So in a production setting, that's one way to think about dealing with hallucinations. Another challenge is LLMs don't have fresh data, right? So we've asked ChatGPT about the @trigger decorator in Metaflow, and it says, as of my last update, there is no official trigger. So how do we think about that, right? So what we can do is schedule and trigger workflows on updated data, which will give you far more relevant results in a timely manner. Next challenge I mentioned is navigating closed versus open source APIs. So we've got such a large families of models these days that we really need to think that through. Oh, sorry. Give me 1 second. Really need to think that through, and you need to have the ability to switch models in and out, right? So let's say you're using ChatGPT, but then you want to change your governance boundary and use Llama 2 for some reason. Then you need to be able to switch these things with as small a migration cost as possible. I will just skip that slide and talk about how expensive fine-tuning is. We know how we all know how expensive deep learning is. Even if we want to fine-tune on a small data set, the models are so big these days that working on the cloud requires a lot of investment. So we really want to help you in thinking through reducing cost. So one example of doing this is using a technique such as QLoRa, which is quantization and low rank adoption, which essentially, the math doesn't really matter, but it uses linear algebra to reduce the number of weights you need, essentially, in order to reduce the costs. And it's going to be more and more useful as we build larger and larger models in this space. So we've talked about some of the challenges and the way forward here. I wanted to wrap up by just letting you know how you can do this at home. You can definitely check out the Metaflow docs at docs.metaflow.org. Do check out our sandbox, because as you see, there's a huge amount of infrastructure that needs to be set up in order for you to even play around with these things. To that end, we've created a sandbox. We've set up all the infrastructure, such as Kubernetes clusters, production-ready environments, the ability to deploy to the cloud, and even the ability to do event triggering and reactive machine learning. So definitely go to outerbounds.com and click on Sandbox and have a play around with it. We have lots of tutorials around this type of stuff, from the audio processing with Whisper to NLP, computer vision, recommendation systems, and would very much like your feedback on all of that. And if you want to chat about any of this stuff, we'll have time for a question or two now, but come and say hi at our Metaflow community Slack at slack.outerbounds.co, and you can DM me at Hugo or ask a question on a public channel, and then a lot of people, including myself, can jump in and we can all have a broader conversation. Once again, I just want to thank you all for your time this morning. It's morning here, and I'm happy to answer a couple of questions now.
Here's a question. Do you recommend integrating the AI system alongside existing systems, or having it independently built and then used via API?
That's a great question. I think it actually depends on what the organizational needs are. And so let me say, for example, if you have a team or an individual that works solely on generative AI stuff, perhaps an API is really important, because if they're building models that rely on other things, you'll want APIs or event triggering between them. But perhaps at the experiment phase, you'll actually find out that the generative AI model, such as Stable Diffusion, actually there's pre-processing where you're using Pandas and NumPy and this type of stuff, and they need to be more interconnected as well. So it definitely depends on the use case, but I think it's a question one should ask when building out any project.
My question is with regards to LLM infrastructure. What, according to you, are the trade-offs with respect to a large cloud provider, AWS, GCP versus open source?
I actually don't understand the question. I mean, because AWS isn't a comparison with an open source model, right? There aren't open source cloud providers. So can the person clarify whether it's open source models versus something like OpenAI's ChatGPT?
We'll give them a second to type in if they'd like. And we had a follow-up question. What other alternatives to a Metaflow are there and what makes it special?
I think probably one of the biggest tools you would have heard of that people compare Metaflow with is Airflow. I think one of the biggest, Airflow is fantastic for data engineering. I think for machine learning workflows, Metaflow is better equipped to deal with the needs of data scientists and machine learning engineers because it's specifically designed for them. Whereas Airflow was and is a tool designed for data engineers. So one example is the ability to do, massive fan outs and parallelization, like fanning out to 1,000 or 10,000 parallel runs of a model to do hyperparameter optimization on Metaflow. You can do immediately, whereas there are a lot more challenges of doing that with something like Airflow. But to be clear, that isn't to say Airflow isn't great for what it's great at. It just wasn't designed for this particular machine learning workflow use case.
And have a
Thanks,
good day.
everyone. Ciao.